Now our topic is fundamental theorem of arithmetic, which is included in class 10 syllabus in the chapter real number. What is that? What is this fundamental theorem of arithmetic? Now, every composite number can be expressed as a product of its primes. Prime means prime factors. And this factorization is unique apart from the order in which the prime factors occur. Now, what is composite number? Now, if a number is exactly divisible by at least one more number other than 1 and itself, then it is called a composite number. For example, 4, 6, 8, 9, 12, etc., etc. So, easily we can do the factorization of this composite number. In that factorization, the prime factors are unique, but the order in which they appear, that may differ. Let us see one example, then it will be more clear. Now, I took one number 42. In the first case, at first I took the factor 2, then it will be 21, then 3, 7. Okay? That means, in this first case, factorization of 42 is represented, or the number 42 is represented in the form 2 into 3 into 7. But you see, in the second case, 2, then I took 7, then 3. Then, this 42 is represented by 2 into 7 into 3. But in this third case, I took the first factor as 3, then 7, then 2. That is, this case, in the third case, 42 is represented in the form 3 into 7 into 2. So, very easily you can see the order of 2, 3 and 7, it differs. But there exist no other prime factors than 2, 3 and 7. The only prime factors in 42 are 2, 3 and 7, whatever may be the order of them. Okay? Now, you can have the question in your mind that if there exists fundamental theorem of arithmetic, is there any possibility of fundamental theorem of algebra? Yes, there are also fundamental theorem of algebra, but which is not included in your syllabus. Just to give the information, I am telling the fundamental theorem of algebra. What is that? Now, every algebraic equation has at least one root, real or imaginary. I repeat, every algebraic equation has at least one root, real or imaginary. Using the prime factorization, we represent, I tried to represent this 336 in a factor tree representation. You see, 336, here the prime factor 2, and if you divide this 336 by 2, this is the number. Again here in 168 there exists a prime factor 2. Okay, and if you divide this 168 by 2, you will get 84. Again there exists a prime factor 2. If you divide this 84 by 2, it will be 42. Then 2 into 21, and at last 21 can be represented in the form 3 into 7. So what is this 336? Now 2 into 2 into 2 into 2 into 3 into 7. Or you can say 2 to the power 4, as 4 2's are there. So 2 to the power 4 into 3 into 7. Now, using this prime factorization or in any other process, we can find the HCF and LCM of some given numbers. How to find the HCF of numbers using prime factorization? Now, the product of the smallest power of each common prime factor in the numbers. I repeat, the HCF of numbers, that is equal to product of the smallest power of each common prime factor in the numbers. And LCM of numbers, that is product of the greatest power of each prime factor involved in the numbers. Each, you see, in case of HCF, each common prime factor, but in case of LCM, there is lack of that word common. Each prime factor, the greatest product of the greatest power of each prime factor in case of LCM, but in case of HCF, product of the smallest power of each common prime factor. As example, you see, I took the number 16, 36 and 144. Just the prime factorization of 16, we can represent 16 is equal to 2 to the power 4. 36 can be represented 2 square into 3 square, and 144 that can be represented 2 to the power 4 into 3 square. Now you see, to get the HCF, at first we need to find the common factor. You see, here is the factor 2, here also 2, here also 2. That means we got the prime factor 2 common in all the three cases. But the prime factor 3 is present in 144 and 36, but not in 16. So 3 is not at all a common factor in all these three numbers. So only 2 is the common factor. Now what we have to take? Now the smallest power of the common prime factor. What is the smallest power of 2 here in all these three numbers? That is square. So the HCF of 16, 36 and 144, that is equal to 2 square. That is equal to 4. But in case of LCM, now we have to take the greatest power of each prime factor. Not only the common prime factor, but we have to take the greatest power of each prime factor. In case of 2, what is the greatest power? 4. So we took 2 to the power 4. Now the prime factor 3, what is the greatest power here in all these three numbers? That is 3 square. So the LCM will be 2 to the power 4 into 3 square, that is 144. And there exists a relation for two numbers only. What is that relation? Now HCF into LCM is equal to product of the number. I repeat, HCF into LCM, that is the product of the HCF and LCM is equal to product of the two numbers. There also I took one example for 24 and 36. 24 is equal to, you can write 2 cube into 3, and 36 is equal to, you can write 2 square into 3 square. Okay, then what is the HCF? Now lowest power of the common factor, you see, for common factor 2, the lowest power is square. So we took 2 square, and for 3, the the smallest power is 1. So we took 3 to the power 1. So 2 square into 3 to the power 1, that is 12 HCF. And LCM, it will be 2 cube into 3 square, that is equal to 72. Now you see HCF into LCM is equal to 12 into 72, that is 864. And the product of the numbers, that is 24 into 36, that is also 864. So it is verified for two numbers, that is HCF into LCM is equal to product of the two numbers. There is also a relation for three numbers. What is that? Now LCM of, suppose three numbers are P, Q and R. So LCM of P, Q, R, that is equal to P into Q into R into HCF of PQR by HCF of PQ into HCF of QR into HCF of PR. Similarly, HCF of the three numbers PQR, what is it? Now P into Q into R into LCM of PQR by LCM of PQ into LCM of QR into LCM of PR. You can take three examples, three numbers to check whether this relation is verified or not. Now we will solve a problem check whether 6 to the power n can end with the digit 0 for any natural number. Okay, that means is there any value of n for which 6 to the power n ends with 0? That means the unit digit of 6 to the power n is 0 or not. Is there any case? We have to check. Let us see the solution. Now 6 to the power n, that can be written as 6 to the power n means 6 means 2 into 3. So 2 to the power n into 3 to the power n. That means what we can see in 6 to the power n, there are only two prime factors. What are they? 2 and 3. But if the unit digit 0 in a number, then that number must have the prime factor 2 and 5. But in this case, you see there is no prime factor 5. And the uniqueness of fundamental theorem of arithmetic confirms us that there will be no such prime factor 5 in the number 6 to the power n. So, it never ends with 0, as there should be a prime factor 5 if the number ends with 0. But in 6 to the power n, there is no prime factor like 5. So, the number is not ends with 0.